Okay, so the next part we have to figure out is how we're going to work with mass, since mass is really what we measure in the laboratory. So it turns out every stoichiometry problem has what we just did in it. It always has some kind of mole to mole conversion. And in order to do the mole to mole conversion, you have to have a balanced chemical reaction. But once you convert to moles, like go moles of A to moles of B, or moles of B to moles of A, doesn't really matter. The way we get between moles and mass is always what we have known as the molar mass. It's the grams per mole. So if you have grams of A and you want moles of A, what you'll end up doing is you'll end up using molar mass to convert. So let's say A is hydrogen. Now hydrogen is H2. So that has a molar mass of 2.02 or 0.18 grams per mole. And if I wanted to get to moles of A, what I could do is I could say grams of, let's say, hydrogen, right? And I would multiply by 2.018 grams of hydrogen for every 1 mole of hydrogen. And then I could do a mole conversion and figure out how many moles of B were being produced. On the other hand, if I had moles of A and wanted to know how many grams of A I produce, then I would also use the molar mass. Again, let's say it's hydrogen, right? And my molar mass is 2.018 grams per mole. Then to get the grams of hydrogen, I would start with moles of hydrogen from my mole-mole conversion, for example. And then I could multiply by 2.018 grams of hydrogen for every 1 mole of hydrogen. So let's use this in an example problem. And you're given 0.455 moles of sodium sulfate, and it reacts with 0.943 moles of carbon. How many grams of carbon monoxide could be produced? And in a lot of these problems, just because I'm not testing this part of it, I'll just give you the molar mass. So that's what that is. The 28.010 grams per mole is the molar mass of carbon monoxide. So how we do this, right? I've given you now 2 reactants. Because I have 2 reactants, what I need to do is convert each of those quantities of reactant into a number of moles of product. So I'm going to pause and let's set up the calculation for going from moles of sodium sulfate to moles of carbon monoxide and moles of carbon to moles of carbon monoxide. So do these calculations. We want moles of CO, oops, oh no, from Na2SO4, and we want moles of CO from carbon. So go ahead and do those, and I'll pop them up on the screen here in a second. Go ahead and pause, and you can do those. Okay, so that's the calculation. Starting with 0.44 moles of Na2SO4, I used my mole ratio from my equation up here, and I find I can make 1.82 moles of CO from the sodium sulfate. Now, when I do the same calculation for carbon, I get 0.943 moles of CO. So now I know which is the limiting reactant, and I know my theoretical yield. So how much could I produce, right? Well, that's in moles. So what I'm going to need to do next is convert that into grams. So I'm going to say grams of CO. That's going to be my moles of CO from my limiting reactant. Times, then I need my molar mass. So I have units of grams per mole, and I want moles to cancel. So the mole goes on the bottom and the grams goes on the top. So I have 28.010 grams of CO for every 1 mole of CO. And then I can do that calculation. And that comes out to be, doing it on my calculator right now, 26.41, and it's 3 sig figs grams of CO. So that answer would come out to be 26.4 grams of CO. That's my theoretical yield. That's how many grams that I could produce, right? That's what they mean when they say that. What's the theoretical yield? So that's my theoretical yield for the reaction. I did want to point out one other thing. Okay, and the other thing is this. You could have done, and this is actually what you'll see in most textbooks actually. You could have done this. Instead of calculating moles of CO, you could have done the calculations directly to grams of CO. So let's say you wanted grams of CO, and this is from Na2SO4. And I would have started with 0.455 moles of Na2SO4. And then I would have said it's 4 moles of CO for every 1 mole of Na2SO4. And then the last step would have been, notice I'm here, right? I've canceled those out. So what I'm left with is moles of CO. I could just tack that last step on. There are some nice, and then I would have calculated. Hang on, let me calculate it, because I already have the one. Oh, sorry, I already have the one for grams of CO from carbon. Oh yeah, this is a mistake here. It's actually grams of carbon. Oh no, that is grams of CO. Sorry. Okay, so I would have done 0.455 times 4 times 28.010, and that would have come out to be 50.98. So really 51.0. I'll just write that, 51.0 grams. There we go. Now, you'll notice that number is bigger than the grams of CO that you get from the carbon, right? So you could have done this calculation, and in this step here, you could have tacked on the grams of CO per mole of CO, grams of CO per mole of CO right here. You could have done that, and those answers would have come out into grams. And there is something really nice about that, because when you're done, you're done. But also, the drawback is you could have stopped a step earlier, because you're going to multiply both of them by molar mass to get to the final mass, and so that's actually one less calculation you have to do. But you do have to write it over again. So there's benefits and drawbacks for doing that. Most of the time in the book, they'll have you go all the way to grams. If you go to moles and stop, I don't consider that wrong, but you still have to calculate the grams. So just keep that in mind when you're looking at the book examples. There's plenty of examples in this textbook, plenty of examples online on how to do these use grams or use mass with mole-mole conversions. Okay, so another real common type of problem, this is probably the most common type of problem in laboratories, is when you have grams of material. For example, you went to a balance and you weighed out some sodium sulfide, you weighed out some sodium sulfate, or you weighed out some carbon. It's a black powder, you just weigh it out. And then you want to know how many grams of product you would make. So we're going to do these as grams to moles to moles to gram conversions. Now, when I say grams to moles to grams, right, not much has really changed other than we've added one more gram mole conversion. And so for this conversion pathway, this is still molar mass that's used between grams and moles, and it's still molar mass between moles and grams. It's just a way that you use the conversion factor that gives you a different result. And this is always between moles and moles up in here. This is always the mole ratio. Okay? And for that, you always need a balanced chemical reaction. So now what we're going to do is do a problem where we do a gram to mole to gram conversion. Okay, so it says if 7.50 grams of sodium sulfide were produced, so we'll identify that that's actually a product over here, right? That's the sodium sulfide. How many grams of carbon were used? And then you're given some molar masses, right? So what we want to do is set up our conversion pathway. Let's think about what we're doing, right? We're given 7.5 grams of sodium sulfide. And we know the first step, because if we're going to do a stoichiometry problem, we need to convert to grams to moles so we can do a mole-mole conversion. That's always in the middle. So the sodium sulfide molar mass is 78.048 grams. So I need my molar mass in here, right, for sodium sulfide. And that'll get me to moles of Na2S. And then from there, we can go to moles of carbon. And then that's going to be my mole ratio. I'll just abbreviate it MR again. It's just easier. And then I'm going to use my molar mass of carbon now to get to grams of carbon. So that is my problem pathway, and I'm going to do this calculation all the way through. It's not a limiting reactant problem. I'm not going to stop at moles. I'm just going to go all the way through from end to end. So I'm looking for grams of carbon. And I have 7.5 grams of sodium sulfide. When you're doing this, you should think, oh, it's got 3 sig figs. And then I need to convert that over to moles. Now, I need to get rid of grams, right? So that means the 78.048 grams is on the bottom, and 1 mole of Na2S is at the top. So I've already checked off this first conversion. I need to then do my mole-mole conversion. And for sodium sulfide, it's 1 mole of Na2S for every 4 moles of carbon. And that's the 1 that's not written there and the 4 that's there. So that gets me to moles of carbon. And then I didn't give you the molar mass of carbon because it's just carbon. But from the periodic table, right, that's 12.011 grams of carbon for every 1 mole of carbon. Okay, so let's go ahead and I'm going to pull up a calculator. And let's go ahead and do the calculation. So 7.50 divided by 78.048, then times 4, and then times 12.011. And you notice how I didn't just do everything at the top and then divide by everything at the bottom. Step by step, I just knocked it off from left to right. It's much easier to do it and not make mistakes. It equals, now I get 4.61677. Did I really say that? Remember all those digits all in a row? 4.61677. I did. Nice. Grams. And 3 significant figures. So that's going to come out. So that's with the grams of carbon. I should do that. And then, oh yeah, I forgot this last cancellation step. And then that's going to be rounded to 3 sig figs. So it's 4.62 grams of carbon. Okay, so again, in these problems, right, everyone has a mole-mole conversion. The only thing that we're adding on top of this right now is molar mass. Use molar mass to get the moles of A, and then you get molar mass of B to get to grams of B. Let's say this was A, right? And this is B, for example. So this is moles of A, moles of B, goes to grams of B. Okay, so one more example problem. Another gram to mole to gram. This one looks a little more complicated, so let's read through it and see what we find. It says 4 grams of calcium carbonate are mixed with 3.5 grams of HCl. So those are the molar masses that are given. CO2, water, and calcium chloride are the products. Calculate the volume in liters of carbon dioxide gas that could be produced. CO2 has a density of 1.2 grams per liter. All right, so let's think about this. It's a chemical reaction, right? So we're going to need to write and balance the chemical reaction. And then we need to look to see, like, what kind of things are we going to be able to calculate from this? Here's the first thing that I usually give students advice to do on a problem like this, right? Think in terms of a gram to mole to gram problem. And if you do that, things start to fall into place. So you have grams of calcium carbonate. You can convert that into grams of carbon dioxide, right? Once you have the grams of carbon dioxide, what can you do, right, to get to the volume? So I'm thinking like this, and I'll just write one of the pathways here, and I'll write the other one down below. I have grams of calcium carbonate, and I can go to moles of calcium carbonate, and then I can go to moles of CO2, and then I can go to grams of CO2. Now, you're given density, and remember, density is a conversion factor between mass and volume. So when it says how many liters of carbon dioxide gas could be produced, that's actually one more step. And for that, we'll use the density. The other ones are the standard molar mass, mole ratio, molar mass, like that. Well, now you're given 2 reactants, right? So what are you going to do with 2 reactants? Well, it's a limiting reactant problem. So you're going to have a similar reaction pathway. We're going to have grams of HCl, and then we're going to go to moles of HCl, and then we're going to go to moles of CO2, because for both of them, it's a limiting reactant problem. We're trying to get to the same product to compare. And then I'm going to go to grams of CO2. And then again, from grams of CO2, when you're looking at this information and you're given density, density is a conversion between grams and volume. So now I can go to liters of CO2. And those are my 2 pathways I have to follow. I'm going to take the grams of each reactant and convert it into grams of product, or you could even do moles like we did for the earlier limiting reactant problems. And at that point, you can determine which one's the limiting reactant. So you can actually just do this portion of the conversion and determine which one's the limiting reactant. And then whichever one is the limiting reactant, you can go on and calculate the volume of the CO2 from it by doing the other part of the pathway. That's this, okay? So I laid it out. We're going to take grams of product formed from the calcium carbonate, and then we're going to do grams of product formed from the HCl. But like I said, you could have just stopped at moles, okay? But I went ahead and did grams to grams. That's actually what's more commonly found, for example, in your textbook. So I'm going to convert grams of grams of calcium carbonate, right? And I have to find the mole. That's 100.09 grams for every 1 mole of CaCO3, and that'll cancel. Then I already balanced the reaction, so I know that it's 1 mole of CO2, that's here, for every 1 mole of CaCO3. And then the last step in what I'm asking you to do here is to calculate the grams. And so I need the molar mass of CO, and that's, oh gosh darn it, that's 44 0.010 grams for every 1 mole of CO2. Now what I want you to do is go ahead and do the bottom one, and when we get back I'll have the answers calculated for both. You can actually see they're on the bottom right hand side of the slide, but we'll go ahead and we'll check those because who knows, I could be wrong. But go ahead and set up for the HCl the mass of CO2 that you would produce. Okay, so there are the calculations. Yeah, it checks out. The ones answered at the bottom are correct. Both have 3 significant figures because I'm starting with 4.00 grams and 3.50 grams. And I get 2 different masses of CO2. And so the theoretical yield, how many grams I can produce, is given by this number here. Okay. So now that I have that, I can take that mass and I can convert it into volume. So the theoretical yield in limiting reactant, right? The theoretical yield is 1.76 grams of CO2. And my limiting reactant is what it came from. So it's this, it's calcium carbonate. Now, the last step, because they're asking for volume, right? Then I can use my density. And my density is given as, in the very beginning of the problem, 1.2 grams per liter. So now we're going to go volume. I'm looking for liters, and I have as my mass 1.75 882, only 3 sig figs, but I want to carry those extra digits for calculation accuracy purposes. This is grams of CO2, and then I need to use my density, and it's 1.2 grams for every 1 liter of CO2. So my grams of CO2 will cancel, and then I'm left with 1.4657. Oh, let me just double check something. Sig figs. Oh, it's 1.20. My bad. So we'll add another sig fig in here. So this is going to be liters of CO2, and I should have 3 significant figures, so it's going to be 1.47 liters of CO2, like that. Okay, just to add on to this example, an example of a theoretical yield, it's kind of some of the things you could watch out for. It says if the CO2 theoretical yield was 1.4657, and it's 3 sig figs, so I underlined the 6 liters, and 524 milliliters of gas, I left the word out, is produced, calculate the percent yield. So you can calculate the percent yield based on the volumes as well. But the only catch is this one is in liters and this one's milliliters. So to actually do the calculation, they have to be in the same unit. So what I'm going to do is I'm going to take 524 milliliters. I want to get it into liters. So I'm going to 524 mLs, right? And then 1 milliliter is 1 times 10 to the minus 3rd liters. I know a lot of you aren't doing it that way, but you can avoid a lot of headaches by just making sure the number of the prefix is on one half and the prefix is on the other half. The letter is on the other half. So that'll come out to be 0.524 liters. And now I can calculate my percent theoretical yield. So I'm going to go percent theoretical yield is going to be 0.524 liters divided by 1.4657 liters, 3 sig figs here, times 100. And that's equal to 35.75 percent. And I only have 3 sig figs, so that'll round to 35.8% theoretical yield. Okay? Now, I just want to point out a couple of things in this calculation, and as I've been doing it through, these are not absolutely critical things, but I want to make sure you understand the implications here. You need to, when you're using a number that you calculated and you continue on in a calculation, use the unrounded number. You'll notice I also did that back here. This is the unrounded number. It turns out every time you round a number, you introduce bias into the number that goes high or low, right? And if you're only doing one calculation or two calculations, you end up rounding up twice, then you end up introducing a significant amount of error. So the goal is to avoid that. So you just use the unrounded number, but you mark the significant figures as you're going along so you can round the final result. When you're all done calculating, round the final result to the correct number of significant figures.